So question 4. Find an expression for what the derivative of density with respect to temperature for an ideal gas. Where D is the density and T is the temperature. Basically, you need to find and make an expression, blah, blah, blah. So why don't I just say in ideal gas world, I mean, if somebody says we're looking for you to take the derivative of density with respect to T, I might, instead of D, I'm going to use the rho, and you're going to hold P and N constant. So I need an expression of density, arguably as a function of T, but it has to come from an ideal gas formula. So I think we know how this works. You get M divided by capital M. Switch these two because you get this M over VRT. That is density. So basically I could isolate that by itself. So you get that. So when I do this derivative, I could just keep it this way. If I purposely now take the derivative of the right-hand side, which is density at the moment, with respect to T holding this constant, then you do the same pressure MRT, right? This is constant, so you bring it out. So you get PM over R, and then we're taking the derivative of 1 over T equals that. So now off on the side, if this was a math one, to get rid of this notation right here, it's understood this partial differential if you write in words this, so you would write if P and N are constant, then the full derivative would turn into the normal D derivative notation. This is partial, but if you state what is the case for your process, the partial collapses to this because you're stating that the full-blown actual derivative, D, can be used. And T to the negative, I'm just rewriting that 1 over T, that'd be dt. So the derivative would be the negative 1 comes down and you subtract 1. So therefore this entity becomes that. So you get negative PM over RT squared equals, that's density. Right? So that's the expression. I mean, just go ahead and show you that. Oh, and I think it's not fitting in. Oh, there we go. So that's essentially, in a rough way, that shows you how you would derive it, right? B, if the temperature, so now part B is saying, given the temperature, pressure, what is the value of the slope? So, and that's the other thing too. What this means is, right here, if you graphed the density versus temperature while P and N were constant, this is what the slope of this graph is doing. So this is not what this graph would look like. This is the expression for what the slope of this graph is doing. So I could go back up here and I could say density equals PM R, and you see how it's 1 over T. So density by itself equals this. If this is all held constant, doesn't this look like y equals, this could be called some constant and 1 over x. So it depends what the constant is. It's not negative. So what is the generic 1 over x graph? It looks something like that, right? This is what the slope at any of these points, what the slope is doing. The slope is changing at a 1 over t squared relation. is what that means. So anyway, you can sub into here and calculate for part B. Yeah, you just put in your numbers here and get what the value of the slope is at those numbers. So you put numbers in here and calculate it. That was for part B. And then part C. Sketch the experimental apparatus, the data chart you would use, and the graph. So, yeah, I already have the graph. This is what ballpark you're doing. So to do this, sounds to me like you'd probably have this. You'd have a constant external pressure. Maybe you just use the atmospheric pressure on the day of your piston. You've got gas in there. And to do this graph, you need to measure the density versus the temperature, right? So you might have an oven that allows you to alter the temperature. So you change the temperature, you record. Now you would have this calibrated in volume, right? So as the volume changes, the density would be the mass divided by the volume. If the gas is constant, the mass will stay constant. The volume, each time you change the temperature, will change the volume, thus the density will change. You graph it, that's what you'd get. So that makes sense. And it's funny, when you look at this, as this temperature gets bigger, the density gets smaller because the volume gets bigger, right? So that makes perfect sense. So that's what question 4 is.